what if just looking at something could actually change it? Seriously. And what if there was, like, software that claimed it could be that observer, predicting everything from, I don't know, wars to your own health?
It sounds like science fiction, doesn't it?
It really does. So today we're doing a deep dive into this whole idea of observation. First, we'll look at the really weird quantum physics angle.
Yeah, the mind-bending stuff.
Exactly. And then we'll unpack this revolutionary algorithm that claims it's cracked the code, basically, using that same idea to forecast global events, even guide cancer treatments.
We'll explore this almost impossible-sounding experiment where you can find live bombs without setting them off.
Without touching them.
And then see how that same core concept, getting information without sort of direct interaction, is popping up in completely new areas.
So yeah, get ready for some surprising facts, maybe a few aha moments. We're going to unpack some really fascinating ideas here. Our mission really is to pull out the key insights from all this, help you connect the dots between quantum weirdness and predictive algorithms. It's definitely cutting-edge stuff.
Definitely is.
Okay, so let's start way back, like over 200 years ago. Thomas Young's double-slit experiment, you hear about it all the time in physics.
Oh, yeah. It's fundamental. It's arguably where quantum mechanics really started becoming this big puzzle. It threw up this massive question.
Yeah.
Why do particles act so strangely when we try to measure them?
Right. Explain that basic setup again. The core weirdness.
Okay, so imagine firing single particles of light, photons, at a screen with two narrow slits in it. If you just let them go through and hit a detector screen behind it without checking which slit they went through, they act like waves. They spread out, interfere with each other, creating this characteristic pattern of bright and dark bands, like ripples in water.
Okay, wave behavior, got it.
And this is the kicker, the moment you put detectors at the slits to see which path each photon takes.
You try to observe it?
Exactly. The moment you try to get that which path information, poof, the interference pattern vanishes. The photons suddenly act like tiny billiard balls, hitting the screen in two distinct clumps right behind each slit. They behave like particles again.
Just because you looked. That's the core mystery, isn't it?
That's the multi-billion-dollar question. How does the mere possibility of knowing the path change the fundamental behavior? It's like reality itself shifts based on observation.
Wild. Okay, so now let's jump forward. 1993. Avshalom, Elitzur, and Lev Vaidman. They proposed this thought experiment that just sounded impossible based on physics back then.
Oh yeah, I was really out there.
Imagine you've got a bunch of bombs. Some work, some are duds. The catch: a working bomb explodes if a single photon hits its trigger.
Right. Very sensitive.
Your job. Figure out which bombs are live without blowing them up. Seems toes impossible, right? Test it directly, and bang goes the working bomb.
Yeah, seems like a catch-22. You can't test it without destroying it if it's functional.
So how do they propose solving this?
This is where they bring in a clever device called a Mach-Zander interferometer. Think of it as a specific way to split and recombine light. You have a photon source, then a beam splitter, basically a half-silvered mirror. It lets half the light pass straight through, reflects the other half.
Okay, splits path.
Splits the path, 50-50 chance. Then you use regular mirrors to guide these two possible paths, let's call them path A and path B, towards a second beam splitter. After that second beam splitter, you have two detectors, detector 1 and detector 2.
Right, so the photon hits the first splitter, could go A or B, then it's the second splitter and ends up at D1 or D2. Classically, you'd expect what? 50-50 at each detector?
Classically, yeah. If photons were just tiny balls, you'd expect a 50% chance of hitting D1 and a 50% chance of hitting D2. But quantum mechanically, it's completely different.
Here comes the weirdness again.
Here it comes. Because the single photon acts like a wave, it doesn't choose path A or path B. Its wave function splits and travels both paths simultaneously. It's in a superposition.
Both paths at once.
Okay. And when these two parts of the wave recombine at the second beam splitter, they interfere. And the setup is arranged so they interfere destructively in the direction of detector 1 and constructively towards detector 2. Meaning, if the interferometer is empty, detector 1 never clicks. Never. And detector 2 always clicks. 100% of the time. That's the baseline quantum prediction.
Okay, baseline, no bomb, always D2, never D1. Now, put the bomb in.
Right. Now, let's carefully place one of our sensitive bombs on, say, path B.
Okay.
So, one possibility. The photon does effectively go down path B, hits the working bomb, and boom, Bomb explodes. We know it was working, but we destroyed it. Not ideal.
Right, that's the outcome we want to avoid.
But here's the truly mind-blowing part. What if the bomb doesn't explode?
Okay.
And what if detector 1 clicks?
Right, D1. But you said D1 never clicks in the normal setup.
Exactly. If detector 1 clicks and there was no explosion, you instantly know with certainty that the bomb on path B is working.
Oh, the photon didn't hit it because it didn't explode.
But the possibility of it hitting the bomb changed everything. Think of the working bomb on path B as a potential observer. If the bomb is functional, its presence forces the photon to choose a path. It can no longer be in that superposition state, taking both paths at once. The wave function collapses.
So the bomb being there, even if not hit, breaks the superposition.
Precisely. If the superposition collapses, the photon must have taken either path A or path B, not both. If it took path B, it would have exploded. Since it didn't explode, it must have taken path A.
Okay, it took path A, so what?
Well, if the photon only travels path A, when it reaches the second beam splitter, there's no wave from path B to interfere with it. Without that interference, the photon now has a 50% chance of going to detector 1 and a 50% chance of going to detector 2.
So the fact D1 could click tells you interference is canceled.
Exactly. Interference was canceled because the superposition collapsed. And the superposition collapsed because there was a working bomb on path B that could have interacted with the photon. So, D1 clicking without an explosion tells you the bomb is live.
That's incredible. You found out the bomb works without the photon ever interacting with it. Interaction-free measurement.
That's the term. You gain information about the object's state, whether it's a working bomb or a dud, without any particle directly touching it. The photon went down path A, but the bomb on path B influenced its quantum behavior. It feels like it breaks all the rules.
It really does. It feels like information is somehow non-local. Like the photon knew about the bomb, even though it went the other way. And you're saying this isn't just theory. They actually did this.
Oh, absolutely. This was experimentally verified just a couple of years later in 1995 in Austria, and then replicated in many other labs around the world. They didn't use actual bombs, obviously.
Probably wise.
Yeah. They used other things that could absorb or detect a photon acting like the bomb trigger, maybe a detector or a piece of glass that might absorb the photon. The results consistently matched the quantum predictions. Detector 1 fired sometimes only when the bomb analog was present and functional on the other path.
So this confirmed that quantum mechanics has this non-local aspect, where something here can be influenced by something over there without direct contact.
That's one way to look at it, yes. The photon's wave function exists throughout the interferometer, and the potential interaction on one path instantly affects the entire wave function, changing the probabilities at the detectors. It's arguably even stranger than things like the uncertainty principle.
Wow. Okay, so what are the implications of being able to measure something without, hitting it?
Huge implications. It basically launched the field of non-destructive measurements or interaction-free measurements. We realized we don't always have to poke and prod something, potentially damaging it, to learn about it.
Like what? Give me some examples.
Well, think about medical imaging. Maybe developing techniques for things like low-dose X-rays. You could potentially get imaging information using photons that could have interacted with tissue but didn't, meaning less radiation exposure for the same result.
That would be amazing for biological samples.
Definitely. Or developing super-sensitive sensors that can detect the presence of something just by its potential to interact. It's also feeding into quantum computing research, new ways to handle quantum information.
And you mentioned something even wilder, counterfactual. Something.
Yes, counterfactual quantum systems. It's pushing the idea even further. Can you transfer energy or momentum without physical contact? People are theorizing about quantum engines that could, nudge tiny objects using these principles without ever touching them.
Okay, my brain hurts a little, but in a good way. The power of getting information without interaction.
Exactly. It's a fundamental shift in thinking.
Right. So we've got this incredibly weird quantum observation thing. Now let's pivot. What if you could, simulate or replace that quantum observer effect with software?
Well, that's the extraordinary claim made by Vadim Chernov, a researcher from Kiev, Ukraine, with his algorithm called RALF1.
RALF1.
He explicitly states that he thinks RALF1 is the key to solving the main problem of quantum physics, the problem of observer. Because, in his view, the observer is our logical thinking.
Whoa, that's a huge claim. He's saying his algorithm is the observer. How?
Well, the way he describes it, he applied RALF1 to model the original double-slit experiment. And he claims the algorithm, just by processing the information logically, produced the same outcome as when a physical observer is present in the quantum experiment and got the particle-like result, not the wave-like interference.
No, he's arguing his code replicates the effect of observation.
That's the argument presented, yes. That the logical processing within the algorithm functions analogously to the role of the observer in collapsing the possibilities in a quantum system. It's linking algorithmic logic directly to quantum measurement.
Okay, let's dig into RALF1 itself then. What's under the hood? How does it supposedly work?
The core principle it uses is actually quite old and well known: Occam's razor.
Occam's razor. Like, the simplest explanation is usually the best.
Exactly that. The principle that says if you have multiple ways to explain something and they all give the same result, you should prefer the one that involves the fewest assumptions, the fewest entities or factors. Keep it simple.
So how does software use Occam's razor?
RALF1 essentially takes complex data and tries to find the simplest underlying pattern or model that explains it. It works by systematically trying to remove parameters or variables that might seem important but don't actually have decisive predictive value. It strips away the noise, the unnecessary complexity, to get down to the core factors driving the phenomenon.
It's like finding the signal in the noise, but using simplicity as the filter.
That's a good way to put it. It's trying to find the most parsimonious, the most elegantly simple explanation or predictive model within the data, which can be incredibly powerful when you're dealing with, massive, messy data sets.
Okay, so if this thing can supposedly act like an observer and uses Occam's razor to simplify, what can it actually do in the real world? What's it predicting?
Well, according to the developer in the source materials, quite a lot. The claim is it can forecast future events across a really wide range of fields.
Such as?
Finance, for example. It's apparently been applied to predict cryptocurrency prices, Bitcoin, Litecoin, others. The claim is it found a recurring periodical process with period 4 years for crypto growth. And it supposedly forecast a major surge even when the input data didn't cover a full 4-year cycle.
A 4-year cycle in crypto. Interesting. What else?
Commodity prices. There's a specific example cited from April 2019 where a forecast for Brent and WTI oil prices made by RLF1 was apparently posted on Twitter.
Okay.
And then a few days later, there were drone attacks in Saudi Arabia and oil prices shot up, which the proponents presented as a successful prediction, validating the algorithm.
So they're claiming it can anticipate these big, unexpected market movers, like black swan events.
That's exactly the terminology used. The idea is that RALF1, by finding these simple underlying patterns, can detect the conditions ripe for these seemingly sudden, high-impact events, making them appear logical in hindsight or even foresight. The goal being to allow for, timely responses.
So finance commodity shocks. Are there examples outside of markets?
Yes. The claims extend to predicting meteorological events, geological ones, medical outcomes, and even military events.
Military events. Okay, that sounds potentially heavy.
It does. The source material highlights a particularly stark application. The claim that RALF1, using Occam's razor on available statistics, could predict the intensity and main target areas of bombings within Ukraine by the Russian Federation.
Wow.
Now, we have to be really clear here. We're reporting on the claims made in the source material. We're not endorsing any political viewpoints or confirming the accuracy independently, but the material does state that the software's utility in this context was apparently recognized at the level of Ukraine's National Security and Defense Council, citing an open letter as evidence.
Right. It's crucial to state that we're conveying the information presented in the sources, not validating these specific, very serious claims ourselves. The idea of predicting conflict areas algorithmically is significant, if true.
Extremely significant. And the need for independent verification for claims of this magnitude is obviously paramount. The source does point to this governmental recognition within Ukraine, but broader scientific validation through peer review would be the standard expectation for such a model.
Understood. But the potential applications aren't all geopolitical or financial, right? You mentioned health.
Yes, and this connects back to that idea of getting the right information to avoid unnecessary interventions, much like the interaction-free measurement idea. We looked at the work of Dr. Belinda Parker, a cancer researcher at La Trobe University.
Right. Breast and prostate cancer.
Exactly. She highlights a really common and difficult problem in oncology. Many patients, say with prostate cancer, get radiation therapy, but a significant number of them would never have actually had their cancer spread invasively even without that treatment.
So they endure the side effects of radiation unnecessarily.
That's the issue. Doctors often can't reliably predict who will relapse and who won't, so treatment tends to be broad, just in case. Dr. Parker's research focuses on understanding why cancer spreads, particularly to bone.
What did she find?
Her team discovered that certain immune pathways are crucial. Cancer cells basically learn to send out signals that tell the immune system, nothing to see here. They effectively shut down special immune signals that would normally fight them off, allowing them to take hold and grow in places like bone.
They trick the immune system.
Essentially, yes. And interestingly, similar immune pathways seem important in both breast and prostate cancer spread.
So what's the goal of her research then?
Two main things. First, to find ways to reverse that immune shutdown, to sort of wake up the immune system to fight the cancer cells trying to spread. But second, and really relevant here, is personalization of therapy.
Avoiding that one-size-fits-all approach.
Precisely. Imagine having a test that could tell you, this particular breast cancer patient is very unlikely to relapse for 20 years with standard therapy, versus this patient has markers suggesting a high risk of spread, so they genuinely need more aggressive treatment, maybe immunotherapy.
That would be life-changing for patients.
Yeah.
Avoiding harsh treatments if they're not needed.
Absolutely. Dr. Parker described achieving this kind of personalization as potentially the highlight of my career. Using that deeper biological information, that predictive insight, to save people from unnecessary treatment, give them peace of mind. It's about refining the information we have to make better decisions.
Okay, so let's try and tie these threads together. We started with a quantum bomb detector that works without touching the bomb.
Gaining information via non-interaction.
And we ended up with an algorithm, RALLF1, claiming to predict oil shocks and maybe even help personalize cancer treatment by simplifying complex data. What's the common ground here? It seems like a leap.
It does seem like a leap, but I think the connection is actually quite profound. It's all about the power and nature of information.
How so?
In the Elitzer-Weidman experiment, the weirdness comes from realizing that information about the bomb state could be obtained indirectly, through its mere potential to interact, fundamentally changing the outcome. It showed that information gain itself can shape reality in unexpected ways.
Okay. Information without direct contact.
Right. Now look at RALF1. Whether or not it truly replicates a quantum observer is a huge question, but its claimed function is to extract the most potent predictive information from complex systems by stripping away irrelevant details using Occam's razor. It's trying to find the hidden signal, the core truth. And Dr. Parker's cancer research is also about finding better predictive information, right? Those immune signals that tell you who is really at risk. Exactly. In all these cases, the goal is to get smarter about extracting and using information, whether it's leveraging quantum non-locality, applying algorithmic simplification, or identifying subtle biological markers. The underlying theme is that understanding and leveraging the right information, sometimes information gained in very non-obvious ways, is key.
So it's about moving beyond just direct cause and effect or simple observation and understanding these deeper, maybe more subtle informational layers.
I think that's a great way to put it. These examples, from the quantum realm to complex algorithms to medicine, suggest that mastering information, finding it, simplifying it, understanding its impact even when indirect, allows us to predict, to intervene, perhaps to prevent negative outcomes, whether that's an explosion, a market crash, or unnecessary medical treatment.
So we've covered a lot of ground, from that 200-year-old double-slit mystery,
Which is still debated.
right, to this modern algorithm claiming to be the observer, and seeing how this concept of observation and information plays out from ghostly quantum measurements to predicting real-world events and trying to fine-tune medicine.
It shows how these really abstract scientific ideas like quantum measurement or even philosophical principles like Occam's razor can potentially have incredibly concrete effects.
Identifying bombs without touching them, forecasting global events, personalizing cancer care. It's quite a spectrum.
And it all hinges on figuring out how to get the most crucial information out of a system.
So maybe the final thought for you listening is this. If the quantum world shows us information can be gained without direct interaction,
Like the bomb experiment.
and if algorithms like RALF1 might be able to find powerful predictive signals by simplifying complexity, what other unseen connections or subtle influences are shaping our world that we just haven't learned how to observe yet?
That's a big question.
Yeah. How could understanding these maybe non-local or information-based relationships change how we tackle problems? Not just big global challenges, but maybe even things in our own lives, our own well-being. What does it mean if we could live in a world where the sudden or the unexpected becomes logical, just because we found a new way to see the underlying pattern?
Something to definitely mull over, how different ways of observing or processing information could change everything.